right now, the most advanced supercomputers on Earth. I mean, machines that process quadrillions of calculations a second are completely failing to predict what the Pacific Ocean is doing. And that multi-billion-dollar blind spot, it might just dictate whether a Category 5 hurricane hits your town this summer. Welcome to Meteorology Matters, the podcast that dives deep into the science, chaos, and stories behind the weather that shapes our world. This show was created by meteorologist Rob Jones. Now let's get into today's episode of Meteorology Matters.
It is incredibly urgent that we have this conversation today. The rules of the game are fundamentally changing.
Yeah, they really are. And look, our mission today is absolutely critical for anyone living near a coastline or, frankly, anyone who cares about how extreme weather impacts our lives, our economy and our safety.
Right, because June 1st is approaching fast.
Exactly. So we are unpacking the brand new 2026 hurricane season forecast. We're going to examine the looming shadow of a massive El Niño in the Pacific Ocean, analyze how the honestly terrifying mechanics of rapid intensification are threatening our coastlines, and then walk through the radical new tools the National Hurricane Center is rolling out to keep you safe.
Which are long overdue, frankly.
Yeah, totally. But I think we have to begin with the raw numbers, right? We need to establish the baseline for what recent atmospheric research is actually projecting for this year.
Yes, the baseline is crucial before we explain why those numbers might be deceiving.
Right, so let's look at the latest meteorological data. They're predicting 11 to 16 named storms, 4 to 7 hurricanes, and 2 to 4 major hurricanes, meaning Category 3 or higher for the 2026 season.
And that includes direct landfalls.
Yeah, they're predicting 3 to 5 direct impacts in the United States. And statistically speaking, there was a 40% chance that we exceed the 30-year historical average of 14 named storms. Oh, and the 2026 storm names list will begin with Arthur, then Bertha, and, continue down the alphabet.
Okay, so you read those numbers. What is your initial takeaway?
Well, when I look at those numbers, 11 to 16 named storms, that sounds incredibly average to me. It falls right in line with the historical norms we've seen over the past few decades.
It does. It sounds completely normal.
Right. Yet, reading through the recent meteorological studies, the research community is characterizing this upcoming season with terms like highly concerning and unprecedented risk. So my question is, if the raw numbers are so perfectly average, why is the scientific community so alarmed?
You are falling into a very common statistical trap there. And it's a trap that, honestly, has cost people their lives.
Wait, really? How so?
Well, we have to draw a hard, uncompromising line between a busy ocean and a disaster. Seasonal forecasts, like the 11 to 16 named storms you just listed, they only tell us about ocean activity.
Just the sheer number of storms that form.
Exactly. They tell us how many localized spinning vortexes of wind and rain might form out in the open water of the Atlantic or the Caribbean. They tell us absolutely nothing about impact.
So a storm staying out at sea counts the same on the spreadsheet as one hitting Miami.
Precisely. Disasters are strictly dictated by atmospheric steering currents and geography. You could have a highly active season, say 25 storms, right?
Yeah, which would be massive.
Right. But if a strong high-pressure system forces all of them to curve harmlessly out into the cold waters of the northern Atlantic, that is a meteorological anomaly. It's fascinating for scientists, but it is not a disaster.
Right. Nobody on land actually cares because it doesn't affect them.
Exactly. Conversely, a season with very few storms where the atmospheric steering currents guide just one major hurricane into a heavily populated coastline, well, that is a catastrophic historical event. In our field, this is codified as the "it only takes one" rule.
I really want to focus on that rule because, statistics can breed this very dangerous sense of complacency.
They absolutely can.
It reminds me of evaluating a baseball team's offense. You might look at a batter who has a terrible batting average. He strikes out constantly. He only gets 3 or 4 hits the entire season.
So on paper, he looks like a non-threat.
Exactly. If you're just looking at the spreadsheet, you dismiss him. But if one of those rare hits happens to be a grand slam in the bottom of the 9th inning of the World Series, that low batting average is completely irrelevant.
Because the impact of that single event defines the entire season.
Right. So how does that translate to hurricane history?
History validates that concept with brutal clarity. To truly understand why the meteorological community is alarmed about an average forecast for 2026, we have to look back at the 1992 hurricane season.
Oh, wow. 1992.
Yes. By all statistical measures, 1992 was remarkably quiet. If you lived in Florida in 1992 and heard the seasonal forecast predicting a low number of storms, you probably felt very secure.
You probably didn't even buy hurricane shutters.
Exactly. And through June, July, and most of August, absolutely nothing happened. The ocean was completely dead. People let their guard down entirely.
And then what happened?
Well, in late August, the very first named storm of the season finally formed. That storm was Hurricane Andrew.
Oh my gosh. And
Yes. It was a compact, incredibly fierce system that slammed into Homestead, Florida as a Category 5 monster. It leveled entire neighborhoods.
I remember seeing the pictures. It literally looked like a tornado had miles wide, just wiped the earth clean.
It stripped the paid-off cars. It fundamentally changed the building codes in the state of Florida forever. Now, that season only produced 7 named storms in total.
Just 7. That's incredibly low.
Right. But no one remembers 1992 as a quiet year. They remember it as the year of Andrew.
Wow. And we've seen that recently too, right?
Yes, we saw the exact same principle play out with Hurricane Michael in 2018. Michael defied the broader seasonal expectations and just exploded into a Category 5 hurricane before devastating the Florida Panhandle.
I remember the wind damage from Michael. It was unbelievable.
The winds were so intense they snapped towering pine trees in half like toothpicks for miles inland. So when atmospheric research presents an average number of storms, you must internalize that the risk to your specific home, your specific family, and your specific town has not decreased by a single fraction of a percent.
Man, that really reframes the entire forecast for you. So, okay, if we are hovering right around that average mark for 2026, what is the atmospheric mechanism keeping those numbers in check?
That is the million-dollar question.
Because, frankly, why aren't we seeing predictions for 25 or 30 storms, given how demonstrably hotter the planet is getting every single year?
Well, the answer to what is suppressing the Atlantic hurricane numbers is actually located thousands of miles away.
Right, in the Pacific Ocean.
Exactly. Recent data from the Climate Prediction Center indicates we are currently transitioning out of a prolonged La Niña phase.
Okay, and where are we heading?
By May through July of 2026, the oceans will likely be in a neutral condition, but the data shows a 62% chance that a massive El Niño will emerge by the June to August window.
Wow, 62%. That's a pretty strong signal.
It gets stronger. There is a 1 in 3 chance it will become a strong El Niño by late 2026, and a 22% chance of it escalating into what climatologists call a super El Niño.
You know, we hear this term El Niño constantly on the news, but I feel like the actual mechanics of it are rarely explained.
They are vast and complex, and they literally govern the weather patterns of the entire globe.
So break it down for us. What is actually happening?
To understand El Niño, we have to look at the baseline normal state of the Pacific Ocean. Under normal conditions, we have incredibly persistent trade winds that blow across the Pacific from east to west.
So that's from the coast of South America, heading toward Asia and Australia.
Right. And these winds act like a massive invisible plow. They physically push the sun-warmed surface water across the ocean toward Indonesia.
Just piling all that warm water up on the other side of the world.
Exactly. And because millions of gallons of warm water are constantly being pushed west, there is a void left behind along the coast of South America.
Right. Nature hates a vacuum. Something has to fill it.
And what fills it is freezing cold water from deep down in the ocean trenches. It wells up to the surface. This cold upwelling is rich in nutrients and supports massive fish populations.
Okay, so that's the normal baseline. Where does El Niño come in?
An El Niño event occurs when those steady easterly trade winds falter. For reasons we are still studying, the winds weaken and sometimes even reverse.
So the plow just stops pushing.
Yes. And when the plow stops, all that warm surface water that was piled up near Asia begins to slosh backward, migrating eastward towards South America. The eastern Pacific Ocean, which is normally freezing cold, suddenly warms up significantly.
You know, that migration of warm water is actually the origin of the name itself, isn't it?
It is.
Yeah, centuries ago, South American fishermen operating off the coast of Peru and Ecuador noticed this periodic, drastic warming of the ocean. And it usually peaked in December, right around Christmas.
Right, and it completely destroyed their livelihood.
Yeah, because the cold, nutrient-rich water was suddenly capped by this invading warm water, so the fish populations completely collapsed. And since it happened around Christmas, they named the phenomenon El Niño de Navidad, the little boy of Christmas, in reference to the infant Jesus.
It is a profound example of observational science predating modern meteorology.
Truly, they had no satellites,
Yeah,
but they knew exactly what was happening to the ocean.
exactly. Those fishermen were documenting a localized symptom of a global atmospheric disruption. Because when that massive, anomalous pool of warm water settles in the eastern Pacific, it completely alters the atmosphere above it.
How so?
Well, warm water heats the air, warm air rises rapidly. This creates massive, towering updrafts of air in a region over the Pacific where they do not normally occur.
Okay, I think I have a good way to visualize this. Imagine a smoothly flowing river, right?
Okay, I like where this is going.
That river represents the global atmospheric circulation, specifically the high-altitude jet streams that guide our weather. Now imagine taking a massive boulder and dropping it right into the middle of that rushing river.
The water is forced to divert.
Exactly.
Yeah.
It creates violent rapids and chaotic ripples downstream. So those massive updrafts of warm air over the Pacific, they act exactly like that boulder.
That is a perfect analogy. They disrupt the jet stream, sending ripples of weather chaos all across the globe. This shift changes the weather map entirely.
What kind of changes are we talking about for you and me on the ground?
Out west, the altered jet stream leads to significantly hotter, drier summers. The soil bakes, the underbrush dries out into kindling, which drastically increases the risk and severity of wildfires across California and Oregon.
Right, and we've seen some horrific fire seasons out there during El Niño years.
Absolutely. Down south, the southern tier of the United States typically experiences cooler but much wetter winters, increasing flood risks. The shifting currents also pull an immense amount of moisture up from the southern plains, dragging it across to the east coast.
So the whole United States feels the ripple effect of that boulder.
Everyone feels it. And while the Atlantic side might see fewer hurricanes, the Pacific Ocean itself gets much wilder. The warmer waters increase the cyclone risks exponentially for Hawaii and the Asian coastlines.
Wow. Okay, so we have this massive boulder in the river disrupting the global jet stream. How does that specifically translate into an average or slightly suppressed hurricane forecast for the Atlantic Ocean and the Gulf of Mexico?
The disruption of the jet stream creates very fast, high-altitude winds that sweep horizontally from west to east across the Gulf of Mexico and the Atlantic basin. We call this phenomenon wind shear.
Wind shear. Okay, and why is that important?
Wind shear is the primary antagonist to hurricane formation.
Right, because a hurricane requires a very specific, fragile architecture to survive. It wants to be stacked perfectly vertical, straight up into the atmosphere, almost like a brick chimney.
Exactly. The structure has to be completely upright.
The heat rises through the center, the air exhausts out the top, and the whole system functions like a massive engine. But if you have strong wind, shear these high-altitude winds tearing horizontally across the top of the storm, it is literally like someone physically kicking the top off that brick chimney.
That's a great way to put it. The exhaust system is broken.
The storm becomes tilted, it cannot organize its internal circulation, and it just gets torn apart before it can mature.
Yes, the wind shear essentially decapitates the storm.
So wait, if El Niño creates massive amounts of wind shear over the Atlantic, and wind shear actively destroys hurricanes, shouldn't we be breathing a massive sigh of relief on the East Coast? Why aren't forecasters telling us to relax?
That assumption right there is precisely why the research community is fighting so hard to communicate the actual danger of the 2026 season. You are looking at wind shear as an isolated variable.
And I shouldn't be.
No, you cannot look at the wind without looking at the water.
Ah, okay.
Yes, El Niño creates wind shear, which acts as a dampening mechanism, but the ocean water temperatures, the literal fuel source for these storms, are behaving in a way that defies historical precedent.
How hot are we talking?
The water in the tropical Atlantic and the Gulf of Mexico is practically boiling. We are seeing marine heat waves that are stretching the limits of our historical charts.
Man, let's visualize the physical interaction happening in the Gulf of Mexico right now, because I don't want you to think of this as a simple math equation where wind shear simply cancels out warm water.
Right, it's not a one-to-one cancellation.
Think of it like a terrifying physics experiment. The Gulf of Mexico is a massive, highly pressurized container. The boiling water temperatures are creating an unbelievable amount of thermal energy. It wants to explode upward into a storm.
It is desperately trying to release that heat.
Exactly. And the global wind shear generated by El Niño is acting like a heavy steel lid, pressing down on that container, keeping all that explosive energy trapped.
Yes, and as long as the lid stays perfectly in place, the storms are suppressed.
But weather's chaotic, right?
Mm.
The wind shear is not constant. It ebbs and flows. So if that heavy steel lid slips even for 24 hours, if a localized pocket of low wind shear develops over the Gulf of Mexico,
All that trapped thermal energy violently releases.
it's terrifying. And the environmental monitoring data, like the extensive water temperature profiling the EPA and other scientific agencies rely on, shows us that these local extremes, these sudden releases of energy, are becoming far more common.
They are, and the scientific term for that sudden, violent release of energy is rapid intensification.
Rapid intensification.
Yes, and frankly, this is the single most terrifying dynamic in modern meteorology. Rapid intensification is the phenomenon where a relatively weak tropical storm explodes into a catastrophic major hurricane in a matter of hours.
Just hours. That's so fast. How does the physics of that actually work?
Well, to understand how this happens, we must look at the thermodynamics. A hurricane is a heat engine. It survives by pulling thermal energy out of the ocean water and converting it into kinetic energy, which is the wind.
Okay, so it turns heat into wind.
Exactly. Imagine a hot air balloon. The burner at the bottom of the balloon represents the warm ocean water. If the water is moderately warm, it is like a standard burner. The balloon inflates slowly, the air inside heats up gradually, and it rises at a steady, manageable pace.
Which is how hurricanes used to form over several days.
Precisely. But the water in the Gulf of Mexico right now is not moderately warm. It is retaining an unprecedented amount of deep, trapped heat. When a storm slips through a gap in the wind shear and encounters this water, it is like strapping a military-grade jet engine into the basket of that hot air balloon.
Oh, wow.
The heat transfer is instantaneous and violent. The core of the storm ingests massive amounts of thermal energy. This causes the barometric pressure inside the center of the storm to plummet precipitously.
And nature hates a vacuum, right? So the air rushes in.
Yes, when the pressure drops that fast, the storm acts like a colossal vacuum cleaner, violently sucking in the surrounding air to equalize the pressure. And that incoming air becomes the destructive wind.
That is just terrifying to picture.
We are talking about storms jumping 2 or 3 categories, going from a manageable 70-mile-per-hour storm to a catastrophic 140-mile-per-hour monster in less than 24 hours.
Which brings us directly to the specific danger zones identified for 2026. Because of this volatile dynamic, the battle between the El Niño wind shear and the incredibly warm water, recent atmospheric research has pinpointed specific high-risk areas along the United States coastline.
Yes, and the threat profile is very concentrated.
The research aggressively highlights the eastern and northern Gulf of Mexico coast. Specifically, the entire west coast of Florida is under an extreme threat profile.
That entire corridor is highly vulnerable right now.
Yeah, this stretches from Pensacola down through the Panhandle and all the way down the western peninsula to Fort Myers, encompassing massive population centers like Tampa, Sarasota, and Clearwater.
And we can't forget the East Coast.
Right. Additionally, the Carolinas are identified as high-risk zones for this particular season. But interestingly, the data indicates that central and southern Texas currently face a lower-than-average risk based on the anticipated atmospheric steering currents.
We really must focus deeply on the vulnerability of Florida's west coast because it perfectly illustrates how meteorological phenomena interact with physical geography to create a disaster.
Because it's not just about the wind speed, is it?
No, the threat there is not just the wind, it is the water. We have to look at the bathymetry, the underwater topography of the Gulf of Mexico right off the coast of Tampa and Fort Myers.
Okay, what makes it so dangerous?
The continental shelf in that specific region is remarkably shallow and gently sloping. It extends miles out into the Gulf before dropping off into deep water.
Why does that matter for a hurricane?
Well, when a hurricane moves across deep ocean water, the intense winds push a massive amount of water ahead of the storm. In the deep ocean, that excess water can simply circulate downward beneath the surface, dispersing the energy.
So it kind of just rolls underneath itself.
Exactly. But when that hurricane approaches Florida's west coast, that mound of water hits the shallow continental shelf. The water suddenly has nowhere to go downward.
Because the ocean floor is right there.
Yes, it is trapped between the ocean floor and the surface. As the storm continues to push forward, that massive volume of water is forced to pile up vertically and surge inland. This physical funneling effect creates a catastrophic storm surge, pushing a wall of ocean water 10 to 15 feet high directly into coastal communities.
And look, beyond the physical geography, there's profound human element here that makes Florida's west coast uniquely vulnerable. It is an absolute demographic nightmare when combined with rapid intensification.
It really is, especially when you consider who is actually down there.
Right, because it's not just the locals who have lived in Tampa for decades and understand the geometry of the coastline. Florida's west coast draws millions of transient tourists every single month.
People who have absolutely no experience with tropical weather.
Exactly. These are families renting beach houses for a week. They do not know the local geography. They do not know which roads flood first. They do not know the designated evacuation routes.
And they certainly do not understand the nuances of the local emergency alert systems.
Most importantly, they lack the historical context to understand how fast a modern storm can escalate.
That lack of context is deadly. Historically, coastal populations relied on a multi-day buildup to a hurricane.
Right, you'd watch it on the news for a week.
Yes, you would watch a storm form off the coast of Africa on the evening news. You would track it slowly crossing the Atlantic for a week. You had days to secure your property, board up windows, buy supplies, and organize an orderly evacuation.
It was a very predictable rhythm.
But rapid intensification entirely shatters that timeline. It breaks the fundamental psychological model of hurricane preparation.
So what does a modern timeline look like?
A disorganized cluster of thunderstorms might form in the middle of the Gulf of Mexico on a Tuesday morning. The local forecast might simply call for heavy rain.
Something you would even cancel dinner plans for.
Exactly. But if that cluster hits a pocket of extreme heat and low wind shear, by Wednesday night, it has exploded into a Category 4 monster making landfall.
That is just horrifying. For a tourist in an unfamiliar rental home, or even a local resident who went to sleep thinking it was just going to be a breezy rain event, that speed of escalation is impossible to react to safely.
You wake up, the water is already rising into your street, the winds are too high to drive safely, and the window for evacuation has completely slammed shut.
Which is exactly why the old ways of warning the public are fundamentally broken. We are facing faster, stronger storms that are threatening highly vulnerable, transient populations with mere hours of notice.
And the agencies are finally adapting to this.
Yeah, to combat this new reality, the National Hurricane Center is radically changing its communication products for 2026. This is a complete revolution in how we visualize and communicate meteorological risk.
It's going to look very different on people's screens.
Let's walk through these new tools, because they will fundamentally alter what you see on your television and your phone this summer. First, the traditional cone of uncertainty, that iconic white shaded graphic we all recognize, is getting a massive upgrade regarding inland warnings.
This is a huge shift.
Moving forward, the graphic will visually incorporate inland tropical storm and hurricane watches and warnings, extending those bright red and blue alert colors far away from the immediate coastline.
This is a vital correction to a long-standing flaw in how the public perceives storm threats. For decades, the visual focus of the forecast cone has been almost exclusively on the coastal impact zone.
Right, everyone just stared at the beach.
The eye of the public was always drawn to the exact point where the center line of the storm was projected to cross the shoreline. But as we saw tragically with Hurricane Helene, a storm's deadly effects do not magically stop at the beach.
Helene was a wake-up call for so many people inland.
Helene maintained its structural integrity far inland, bringing catastrophic torrential flooding and devastating wind gusts to mountainous regions hundreds of miles away from the initial landfall.
So this new map tries to fix that visual bias.
By extending those vivid watch and warning colors deep inland on the official graphics, the National Hurricane Center is actively fighting coastal bias. They are forcing the public to visually recognize that a hurricane is not merely a coastal event.
It's a sprawling regional hazard that can obliterate infrastructure and cause immense loss of life far from the ocean.
Exactly.
And it is not just the inland warnings that are changing. Beginning in 2026, we are going to see the introduction of experimental ellipse cone.
This involves a profound shift in the underlying mathematics of the forecast.
Historically, the National Hurricane Center created the cone by drawing circles along the projected path of the storm. Moving forward, they will use ellipses, elongated ovals.
Right, and the math behind those ovals is much more comprehensive.
This new mathematical model will account for historical errors in both the direction of the storm and the speed of the storm. Because of this complex calculation, the new experimental cone will cover 90% of the forecast track possibilities.
Which is a massive jump in coverage.
Yeah, to put that into perspective, the traditional cone we have relied on for years only covered 67% of the statistical possibilities.
To truly appreciate why this change is necessary, we have to look at the psychology of warnings and how the human brain processes visual information.
Okay, what was wrong with the old cone psychologically?
The old 67% cone had a massive psychological flaw. When human beings look at a graphic with a strictly defined line or border, our brains naturally crave certainty. We want a simple binary, safe or dangerous.
So if you're outside the line, you think you're fine.
Exactly. If your particular town was located just 1 mile outside the skinny black line of the old forecast cone, the psychological response was overwhelming relief. You mentally checked out. You thought, I am outside the cone, therefore I am totally safe.
Even though the storm is hundreds of miles wide.
Right. Mathematically, that was a dangerous illusion. There is always a 1 in 3 chance, a 33% probability, that the exact center of the storm would track completely outside of that designated cone.
Which is a huge margin of error when you're talking about a Category 4 hurricane.
Furthermore, it completely ignored the fact that the life-threatening impacts of a major hurricane, the storm surge, the outer rain bands, the tornadic activity, extend hundreds of miles outward from the center point.
I think the best way to visualize this difference is to imagine driving a car on a dark, winding, unfamiliar road in the middle of the night.
Oh, I like this. Or,
The old 67% forecast cone was like driving that road with only your low beams turned on. You can see the most likely path right in front of you. You feel relatively confident about the immediate stretch of asphalt.
but you're missing everything else.
Exactly. Your low beams completely miss the edges of the road. They miss the sharp drop-off on the left. They miss the deer standing quietly in the ditch on the right. You have an illusion of safety because you are ignoring the periphery.
And what does the new cone do?
The new 90% ellipse cone is like finally reaching up and turning your high beams on. The illuminated area is dramatically wider. The beam stretches further forward and spills out into the tree line.
So you see the real danger.
Right. Now, initially, this might look a little more intimidating because you suddenly see much more of the surrounding landscape and all the potential hazards waiting in the dark. But it is giving you a much truer, much more accurate picture of your actual risk environment.
That is a phenomenal way to explain it. The new 90% ellipse model achieves exactly that. It changes the psychological impact of the forecast by illuminating the broader reality.
It forces you to pay attention.
When the public sees a much wider cone, an elongated shape that encompasses a vast array of track possibilities, it strips away that false sense of absolute safety for the people living on the margins of the forecast. It forces a broader regional state of readiness.
And this isn't just an Atlantic upgrade, is it?
No, we must remember that the El Niño dynamics we discussed earlier do not just impact the Atlantic. They significantly increase the cyclone risks in the Pacific Ocean.
Right, because of the warmer water sloshing eastward.
Because of this shifting threat profile, Hawaii is also receiving major meteorological upgrades for 2026. The islands are getting brand new dedicated storm surge watches, specific storm surge warnings, and highly detailed peak storm surge graphics tailored to their unique volcanic topography.
Which is so critical for an island chain.
Absolutely. The National Oceanic and Atmospheric Administration is ensuring that as the atmospheric patterns shift the global risk profiles, our communication and alert tools evolve simultaneously to protect vulnerable populations.
We have spent a lot of time looking deeply at the specific mechanics of the 2026 season. We understand the El Niño factor, the terrifying reality of rapid intensification in the Gulf of Mexico, and the new high beam warning tools. Now, I really want to take a step back. Let's zoom out and look at the broader climate horizon.
I think that's important, yes.
With global ocean temperatures consistently breaking historical records year after year, it begs a terrifying question. Are the physical paths of these hurricanes permanently shifting? Like, are the storms actively hunting for warmer water?
It's a complex question, and the answer is nuanced. Recent climate modeling studies show definitively that hurricanes are fundamentally changing in their composition.
Meaning what's inside them?
Yes, they're getting measurably stronger, and they're carrying significantly more moisture, making them exponentially wetter and more prone to catastrophic flooding.
Right, we're seeing these massive rain bombs being dropped on cities.
But the actual shifting of the physical tracks where these storms physically travel is a fiercely debated topic in the scientific community.
Let's break this down by looking at the genesis location first. Where are these storms actually being born? The data over the last few decades shows a clear trend. Storms are increasingly forming much closer to the United States coastline.
And this data point directly exacerbates the crisis of rapid intensification and reduced warning times that we just discussed.
How far out did they used to form?
Historically, many of the most devastating long-lived hurricanes were what we call Cape Verde storms. These systems originated as atmospheric waves rolling off the west coast of Africa near the Cape Verde Islands.
So literally an ocean away.
Yes, they would slowly organize and take a week or sometimes 10 days to march thousands of miles across the open Atlantic Ocean. That vast distance gave forecasters incredible lead times. They could observe the storm, model its path, and warn the United States days in advance.
But that map is shrinking now.
Drastically. As the oceanic waters closer to the North American continent absorb massive amounts of excess heat, the map of hurricane genesis is shrinking.
So they're popping up right in our backyard.
Areas in the Caribbean and the Gulf of Mexico that were previously too cool or too atmospherically hostile to trigger cyclogenesis, which is the physical birth of a tropical cyclone, are now boiling breeding grounds.
And when a storm is born just a few hundred miles off the coast of the Carolinas, or right in the middle of the Gulf of Mexico, you lose those precious days of crucial lead time.
Exactly. The storm forms, intensifies, and makes landfall in a single, terrifying sequence.
But what about the actual tracks of the storms once they form? Are they shifting east toward the open ocean or west toward the coast?
When researchers analyzed the last 50 years of landfall data, they found no massive east-west shift for United States landfalls.
Oh, really? It stayed pretty steady.
Yes, the geographic distribution has stayed remarkably, almost stubbornly consistent. Roughly 2/3 of all landfalling storms hit the Gulf of Mexico coastline, and 1/3 hit the Atlantic coast.
However, when researchers looked at the data on a north versus south axis, they found something deeply significant, right?
They did. There is solid empirical evidence of a slight but measurable southward shift. On average, storms are reaching their absolute maximum intensity about 21 miles further south than they did in previous decades.
That 21-mile southward shift is a fascinating data point because it reveals the hidden mechanics of climate change. It is not happening arbitrarily.
No, it is likely driven by the concept of differential heating.
Explain differential heating for us.
Well, the subtropical Atlantic, meaning the ocean water further north, is actually warming at a faster rate than the deep tropical Atlantic near the equator.
Okay, so the top part is getting hotter faster than the bottom part.
Exactly. And because the northern waters are heating up faster, it alters the atmospheric pressure gradients across the entire basin.
Which changes the wind.
Yes. This differential heating subtly changes the regional wind patterns, creating an atmospheric environment that slightly suppresses the storm tracks southward, pushing them closer to the Caribbean islands and the northern coast of South America before they curve north.
But discussing how climate change impacts steering currents brings us to one of the most compelling, confounding, and frankly terrifying contradictions in modern meteorological science.
Ah, yes. The model versus reality problem.
This is the part of the research that genuinely left me in disbelief. We are talking about a massive scientific paradox.
It really is a profound divergence.
Look, the world's top climate models, the unbelievably complex software programs running on the most advanced supercomputers on Earth, have a very clear prediction for the future. They calculate that as global greenhouse gases increase and the planet continues to warm, the Earth will fundamentally transition into a permanent, baseline, El Niño-like state.
That is what the computers insist will happen.
And if those supercomputers are correct, a permanent El Niño state would create massive, persistent wind shear over the Atlantic. Theoretically, this would alter the steering currents and consistently push hurricanes further east, guiding them harmlessly out into the open ocean and away from the United States coastline.
Which would be a very welcome outcome for the U.S. coast.
Right. But observed reality over the last 40 years shows the exact opposite. The actual physical oceans are not moving toward El Niño. They are showing a pronounced, measurable trend toward a La Niña-like state.
It is a profound and highly controversial divergence in the scientific community. We are looking at a fundamental disagreement between theoretical physics and empirical observation.
How can the computers be that wrong?
Well, the computational climate models are marvels of human ingenuity. They divide the entire Earth's atmosphere and oceans into millions of three-dimensional grid boxes.
Like a massive digital grid over the whole planet.
Yes, and they use incredibly complex physics equations to simulate the transfer of heat, momentum, and moisture between every single box. These models forcefully insist that because the ocean absorbs heat differently than land, an El Niño dominant state with a massively warmed eastern Pacific is the only logical thermodynamic outcome of a warming world.
But the ocean isn't listening to the math.
Not at all. When we look at the empirical data, the actual hard temperature readings pulled from thousands of ocean buoys, deep water probes, and continuous satellite monitoring over the past 4 decades, the Pacific Ocean is behaving like a persistent La Niña.
It's stubbornly holding on to that cold water.
Exactly. The cold tongue of upwelling water in the eastern Pacific is not vanishing as the models predicted. It is persisting, and in some metrics, it is actually strengthening in ways the supercomputers simply do not comprehend.
I really need to pause here because the magnitude of this blind spot is staggering. You are telling me that the most advanced supercomputers on Earth, the exact machines we rely on to project the future of our climate, the machines that dictate global policy and trillions of dollars in infrastructure planning, have been predicting the exact opposite of what the physical ocean is actually doing when it comes to the most important weather mechanism on the planet.
Yes, that is exactly what the data shows.
That is just mind-blowing.
And rather than viewing it as a failure, we must view it as a humbling reminder of the fundamental chaos and immense, almost unfathomable complexity of meteorology.
Because nature is infinitely more complex than code.
A supercomputer, no matter how powerful, is ultimately only as good as the human assumptions programmed into its base algorithms. The ocean-atmosphere coupled system is so vast, so incredibly intricate, that it relies on millions of microscopic interactions.
Things we can't even properly measure yet.
Exactly. Our models struggle immensely with feedback loops. For instance, how do changing temperatures alter the formation of specific types of low-level clouds? How do those clouds reflect sunlight?
Or how pollution plays into it.
Right. How do microscopic atmospheric aerosols alter rainfall? How do microscopic changes in ocean salinity affect deep water currents that take thousands of years to circulate?
So the models just can't see the full picture.
The supercomputers clearly have blind spots regarding these localized feedback loops. As scientists, we must prepare the public for the ocean we actually have, not the ocean the computer models arrogantly predict we should have.
The implications of that are staggering. If observed reality continues to completely defy the supercomputer models, and the global climate stays locked in this persistent La Niña trending pattern over the long term, what does that mean for the physical hurricane tracks?
It means we face a much higher threat level.
It means the exact opposite of the supercomputer's optimistic prediction. It means the Caribbean Sea and the Gulf of Mexico will likely see a massive, sustained increase in hurricane activity, while the Atlantic coast sees very little change.
And it concentrates the highest levels of danger squarely on regions that are already incredibly vulnerable to storm surge and rapid intensification.
Which brings us back to those shallow coastal shelves we talked about.
Exactly. And even when we do experience periodic El Niño years, like the one forecasted for 2026, we cannot view them as resets.
What do you mean by a reset?
We must remember that El Niño's excess heat does not simply vanish into the freezing void of space at the end of the year.
Oh, because of the greenhouse effect.
Yes. Because of the steadily increasing concentration of greenhouse gases in our atmosphere, acting like an insulating blanket, the Earth cannot effectively radiate that excess heat away before the next cycle begins.
So where does the heat go?
The immense thermal energy from a strong El Niño year gets trapped in the deep ocean. It pushes the entire baseline temperature of the Earth permanently upward.
Like a ratchet that only turns one way.
It is a one-way ratcheting effect. Every single strong El Niño event leaves the global ocean permanently warmer than it found it.
But even a quiet year leaves us worse off for the next one.
This continuous trapping of heat leads to broken climate records year after year, and it provides an ever-expanding, boiling reservoir of fuel for future hurricane savings.
It is a sobering, incredibly heavy reality. And, it brings us to a final chilling implication of all the atmospheric research we have discussed today. We really need to look at how all these compounding factors, the warmer water, the shifting genesis points, the rapid intensification converge to change how we actually live on the coast.
The physical reality of coastal living is fundamentally changing.
Because if hurricanes continue to form closer and closer to the coastline, robbing us of the long-track warning times.
Yes.
And if the terrifying mechanics of rapid intensification, fueled by a literally boiling Gulf of Mexico, can turn a disorganized rainstorm into a Category 4 or 5 monster overnight, the entire concept of days of warning might become a relic of the past.
We are losing the luxury of time.
We may be moving rapidly out of an era defined by highly organized, multi-day, state-run coastal evacuations. We might be moving into a terrifying new era where shelter-in-place becomes the only viable option simply because the storm forms and escalates far too fast for millions of people to physically run.
The logistics of mass evacuation are already incredibly strained.
Think about the logistical nightmare of a major metropolitan area. You simply cannot evacuate a city the size of Tampa or Fort Myers in 12 hours. It is physically impossible. The highway infrastructure cannot handle it.
The interstates would instantly become parking lots.
You would have millions of people trapped in their cars out in the open, sitting in gridlock, when the catastrophic winds and the 10-foot storm surge finally arrive. That is the loaded spring we are dealing with. That is the dark, high-stakes road we are driving down with our new high-beam forecast cones.
We need to understand the mechanics of the ocean, respect the limits of our forecasting tools, and be prepared like never before.
Well said. Please remember to like, follow, comment, and rate the podcast. It really helps us get this vital meteorological information out to the people who need it most. And be sure to follow meteorologist Rob Jones for continuous expert updates throughout the season. You can find him on Instagram by searching meteorologist, on TikTok at TV Meteorologist, and on YouTube by following Rob Jones Hurricane, where you can also find the full Meteorology Matters podcast playlist to catch up on previous episodes. You've been listening to Meteorology Matters, created by meteorologist Rob Jones. Thanks for listening, and remember, meteorology always matters.